I'm very pleased to welcome Stephen Kane to today's CHEOPS webinar talk. And we are very grateful to Stephen for connecting from all the way from San Francisco. So it's 1 o'clock in the morning for Stephen to give this talk about a very eccentric planet. So Stephen is originally Australian, and he also finished his PhD in University of Tasmania on the topic of spectroscopic and photometric study of gravitational microlensing events. But he has since been working on both radio velocity and transit studies, as we will see in this talk. Stephen is currently at the San Francisco State University. So please, Stephen, go ahead.
Thank you, Alexis, for that introduction. I hope everybody can see my slides okay. And there's some background.
Wait, if you can ask everyone to switch off their microphones, that would be helpful. Especially Christina, I think, making some noise.
Okay, well, anyway, I shall carry on. So I'm going to be talking to you all today about not just any old eccentric planet, but what appears to be the most eccentric planet that we know about. And this is part of a large collaborative effort that has been going on for some years. And so what I'm going to be showing you is part of an obsession of mine for the past few years, and some potentially exciting results, and something which may provide a very nice target for CHEOPS. So to give you an idea of my obsession of these kinds of objects, I wanted to start with this slide, which is showing the eccentricity of exoplanets as a function of the orbital period. I'm sure many of you have seen this plot before, and one target in particular has been studied in great detail from the known eccentric planets, and that is this one near the top. I hope you can see that actually on my screen. It's blocked a little bit by the software, but it's 8606, has an eccentricity of 0.93, and that one, as I said, has been studied quite a bit, and that's due in no small part to the fact that it's known to transit its host star. This one was found actually to undergo a secondary eclipse first. There was additional radial velocities for this planet that were obtained by Greg Laughlin and his collaborators, and they predicted quite precisely a time of secondary eclipse, and they were able to get time using Spitzer and observe that eclipse take place. The reason is because it has a very close passage to the star during the time of when eclipse could occur. So it had a high eclipse probability rather than a transit probability. But follow-up observations during the inferior conjunction, when it's between us and the star, showed that it transits as well. So that's been a very exciting planet over the years for us to look at. But in general, what we're trying to do is see how many of the known radial velocity host stars transit, which is, of course, the premise of a lot of the science of what CHEOPS will be doing. And there's a bit of a fundamental problem that we face when we try and do this kind of work. And that problem is shown in this slide here, which is, of course, the issue of calculating the transit ephemerides. And the transit ephemerides is something that we can calculate from the radial velocity data and the orbital solution that we obtain, and then we propagate that out to some time when we're actually going to be able to obtain photometry during the time of a transit window. Now, I want to be clear what I mean when I say transit window here. What I mean is the transit window can be approximated as the uncertainty on the transit midpoint, but in addition to that, you have the transit duration. And so that creates a transit window in which you could feasibly observe an entire transit from beginning to end. And what I've shown here in this diagram is that the size of the transit window, it's unsurprising really that scales with the orbital period. The short period planets, we usually observe many orbital periods or orbital phases of the planet, and so we constrain the orbit quite well. And so at least initially, the time of transit can be well known. As we go out to longer orbital periods, you see that the size of the transit window becomes comparable to the orbital period. And when you're in that situation, you have to confess to yourself that you don't really know where the planet is in its orbit. And so you don't know when a transit window could occur to any degree of certainty at least. And what we would like to do is be able to somehow shift everything down into this blue region, this blue shaded region I've now shown on the plot. And you'll notice that that blue shaded region I've shown up to a transit window of 1 day, which seems quite generous. But one of the things to keep in mind is, like I said, the transit window, the way I've defined it, includes the transit duration. And so for some of the longer period planets, the duration can be quite large. It can be 12 hours, 15 hours. And so as long as the transit window is dominated by the transit duration and not by the uncertainties on the midpoint, then you're in a good situation, because it means that even if you're doing ground-based observations from a particular site, you could know when the ingress is going to occur or the egress is going to occur. So this is what we're trying to do as part of the TERMS project. So the TERMS project is something I've been running for about 5 or 6 years now, and it's trying to do exactly what I've described in terms of trying to push these transit windows down into an area where we can then follow them up. And to do that, we get a lot of follow-up radial velocity data. We normally try to use the same instrumentation that was used to get the discovery data. For example, if there was a planet which was discovered using data from Carly, then we were trying to use Carly data to minimize the impact of having an offset in the radial velocity data that would be an extra free parameter and add uncertainty to our transit times. So we've been collaborating with a lot of people around the world to get these data and then following them up. Now, following them up, we've been using a variety of ground-based telescopes, and one of the more recent additions to our arsenal of photometric follow-up has been the Las Cumbres Observatory global network of telescopes, because that allows us to get pretty much continuous coverage of targets all around the world. They have deployed their telescopes in the southern hemisphere, not completely in the northern hemisphere, but allows us to get a lot of the coverage we need, because a lot of the times the transit window may not match up with our particular longitude. So one of the other instruments which has served us very well has been MOST, the Canadian Space Telescope, and I'll talk more about that in a moment. First, I want to give an example of why this is so important and what kind of improvement you can make. And one of the things that we do is we look at targets which may have lay dormant for quite some time. By that I mean you have some radio velocity data which has been published, several years have gone past, and the transit ephemeris has gone cold. By that I mean it becomes one of those cases in the plot I showed earlier where the size of the transit window is now exceedingly large and you don't really know where it is. In those cases, you can do an extraordinary amount with a relatively small amount of data, because if you obtain just a couple of radial velocity measurements, then you're immediately vastly increasing the time baseline of the observations, and it dramatically reduces the uncertainty on the orbital period. So in this slide here, I'm showing an example where we had one case, it was a 140-day period planet, and when we calculated the size of the transit window just based on the published orbital parameters, we had a transit window of around about 82 days, which once again is one of these cases where it's comparable to the orbital period of the planet. But just obtaining 4 more radial velocity measurements during one of the orbits, then you're immediately reducing the size of that transit window by a factor of 25, and that is mostly the reduction in the uncertainty on the orbital period, which then propagates forward to when you're actually going to acquire the observations. Now, I want to tell you briefly how we do this internally within terms, because this is something that I think is really useful to CHEOPS. This is something that I've spoken to Daniel Bayless and a few of the other folks in Geneva about how we're doing this at the moment. And that is that we have, for the terms collaborators, we have an internal web page which the observers can log into. And the web page contains all of the information that observers would be interested in. It includes things like the transit probability, the expected depth of the transit, it has links to the ephemeris as well as finding charts, all those kinds of things. And in addition to that, we have an automated email system which gathers information about transit windows which are coming up over the next couple of weeks to give observers a heads up. Because, of course, we don't expect observers to just be hanging out at this website every day. That's just not going to happen with everybody's busy schedule. So we have this email system which will alert observers about something exciting which is coming up. And that's all completely automated system. It has to be with this amount of data. So the last column on this table, which you can see in front of you, gives the status of that particular target, and that can be either open, which means that nobody currently knows if this target transits or not. It can be closed, which means our group or somebody else has ruled out a transit, or it has the category of transit, which means it's known to transit, which is the case for 8606, which I have marked there. We know that one transits. To give you an example of one of the other ones, which we looked at a couple of years back, and that was this one here, which is HD 114762, the 84-day period planet in the eccentric orbit discovered by Latham et al. A few years back, quite a few years back. And that was a case where we accumulated quite a bit more radial velocity data. At that time, we were still getting radial velocity data from Lick. And we put together the 19 years worth of Lick radial velocities that we had and produced a very, very strong ephemeris. Our next step was to do the photometry, but we're very fortunate to have one of our collaborators be Greg Henry. And the reason I say that's very fortunate is because Greg Henry has been monitoring a lot of the known exoplanet host stars for many years. He has access to the automated photoelectric telescopes and They truly are automated in the sense that he provides a list of targets to these telescopes, and they will just routinely go and observe these targets when they're visible at least once per night. And so over time, he's accumulating this time series of photometry. And that means that he's getting fairly low cadence data on a lot of these targets over long time scales, but when you fold them on some particular time scale, like the orbital period of a planet, then you can see some interesting things. So the great thing about having a collaborator like Greg is that I can go to Greg and say, look, we have a great new ephemeris for this target, HT 114762. Can you observe it during the next transit window? And Greg will likely come back to me and say something like, well, actually, I've been observing that star for over a decade now, for 13 years, and let's just fold my data and see what we get. So that's what we did in this case. He did actually get some more observations as well, but he had already been observing this star for many years. And so we were able to immediately rule out a transit for that particular target, and then we changed the category to closed for this one because we had ruled it out. So we've been doing those kinds of targets systematically over the years, ruling things out one by one. There was another one that we did fairly recently, which was quite interesting because it was one of the very first exoplanets that was discovered here at San Francisco State, actually. And that's the planet orbiting 70 Virginis. And that, for that one, we combined a lot of radial velocity data from various sources. We had a lot of new Keck data, and we looked very carefully for other planets in the system. We had a lot of photometry, ruled out a transit. We had such good constraints on the orbit. We were able to do some orbital stability simulations to see if there was any chance of having, say, terrestrial planets within the vicinity of the known planet that's orbiting there. So we did a lot with that data, and that was a lot of fun to do. So that was a paper which came out last year. But like I said, we've been doing this for a number of years now. I've had various students working with me on some of these targets, and initially the whole purpose of terms was to, as I said, go through the list and systematically rule out transits. But we ended up doing a lot of other things besides. A lot of it was to do with transit predictions, but when you're getting additional radial velocity data for these systems, you end up either ruling out additional planets, like in the case of 70 Virginis, or discovering additional planets. And we've done that in a few different cases where we've found additional longer period planets in the data that you just needed the longer time baseline in order to uncover. I also mentioned already that in the case of 70 Virginis and otherwise, we've been using these refined orbits to do a lot of work on orbital dynamics, and I've had a few publications discussing that. But what I want to do now is talk about the main thing that I want to tell you about today, and that is about the possibility of phase variations. Phase variations for highly eccentric planets is something that also requires you to understand the orbit very well. And if you do understand the orbit very well, then it can really pay off, because eccentric planets have a great variation in the distance between the planet and the star. And that makes an enormous difference to the amount of reflected light that you see. And so I'm going to show you an example of that. So going back to this diagram, which is showing 8606, and a lot of people, when asked, which is the most eccentric planet, a lot of people say 8606 actually, because it is so well known. And I recently wagged the finger at the Kepler folks because they did a little publicity thing where they asked people for their favorite planets. And one of the ones they listed was the most eccentric planet, 8606. And I said, it's not the most eccentric planet. It's just the most well-known eccentric planet. Because if you look right up the top, almost hidden behind the exoplanets.org logo, which is up there, you'll see that there's HD 20782. And HD 20782, it was discovered about 10 years ago by the Anglo-Australian Planet Search folks. And it was something that has really been somewhat of an obsession of mine over at least the past 5 years, trying to understand what this means for a number of reasons. For one thing, when I looked at the radial velocity data that was published, it always really bothered me because the orbital eccentricity that they used was 0.95, but it was based on one data point, really. There's that one particular data point that you can see with about minus 200 meters per second below the 0 point there. And I always looked at this plot, and if I covered that point over with my hand, I'm not sure that I or many other people would believe such a high eccentricity. And so when it's driven by one data point, I just wasn't quite convinced. So I really wanted to solve this mystery and understand if this is exactly what we thought it was. So we followed it up. We got some more data. I collaborated with the folks at the Anglo-Australian Planet Search and asked them to continue to get more data for me. And as they were getting more data, I was predicting times when the periastron would occur, because that was the point, that we needed the data points during the periastron passage in order to do this. So that's what we did, and this is how the radial velocity data eventually panned out. And you'll notice that there are some, as well as the red points, which are from the AAT, there are some black points at the end there during the last periastron passage, which are from an instrument called Paris, which you may not have heard of. Not many people have, because it's only just starting to produce science quality data. And 20782 was one of its first targets. Having the longitude of India is always extremely helpful, because there are very few good sites, very few telescopes at that particular location. But they were able to cover the periastron passage for us extremely well, the most recent one. And that was during January of 2015. And here's a zoom of the periastron passage. And there you can see that once we've folded the data, that we have a couple of the AAT points from that original discovery data, and then some additional ones from the follow-up periastron passages, and then the additional data from Paris. And so that allowed us to obtain a Keplerian orbital fit, which we really did believe. And that resulted in, lo and behold, the orbital eccentricity of 0.96. So the original prediction was pretty close, and actually turned out to be slightly more eccentric than we originally thought. So now I'm going to show you the implications of this. And to do that, this is a representation of the orbit of the planet. The orbit of the planet takes around about 600 days. And here in this figure, I've divided it up into 200 separate points, separated by time And that means that each point that you see there is separated by about 3 days. And it really shows the dramatic change you have during the periastron passage. So here are the orbital parameters that we have for the planet. Like I said, eccentricity is around about 0.96. The mass of the planet, by the way, is about 1.5 Jupiter radii. And another thing that we did, which I'm not going to present here, but is in our publication, is that we used Hipparcos, the re-reduced Hipparcos astrometry to rule out a face-on orbit, because the semi-major axis and the distance to this star is sufficient that we can rule out a face-on orbit. So it means that whatever this object is, it's not stellar, and it's probably planetary. So the closest approach it makes to the star is about that of a hot Jupiter. And that was very, very intriguing to me, because it means that if the distance between the planet and the star along the line of sight is around that of a hot Jupiter, then that means that it has the transit probability of a hot Jupiter, which is around about 10%. So that made it a very compelling target to try and see if there's anything strange going on during the periastron passage. So we predicted a time for the passage. Only had uncertainty of a few hours because of the periastron passages we had observed. We had very tight constraints on the time of transit. But this is a very difficult target, because it's a bright target, but the main thing is that the orbital period is close to 18 months, which means that you're only going to be able to have an opportunity, usually, to catch a transit window every other passage, because on the next passage, the star will likely be behind the sun, and so we won't be able to see it. And so I didn't want to wait 3 years until my next opportunity to observe this, and so I didn't want to take the risk of observing it from the ground, where all kinds of things can go wrong, most notably the weather. So at that point, I contacted Jamie Matthews, and Jamie was very excited about this target. And I only needed 24 hours to observe this during the transit window. But as I said, Jamie was very excited, and he decided that he really wanted to devote some time to this. So he had most observed this target for a full week. And the time that was covered by that is essentially shown in this box. Like I said, the distance and time between each of those points is about 3 days. And so from the time when the planet enters this box at the bottom left, and then exits the box at the top, is around about 7 days. So that was the total coverage that we obtained, which means that during the course of those 7 days, we covered the time of inferior conjunction, the periastron passage, and the superior conjunction right on the other side. So we managed to cover all three of those events. The data that we got showed that the planet doesn't transit. So here's all of the MOST data. This is the binned MOST data, and it shows pretty decisively that the planet doesn't transit. And when Jamie sent me the data, there was something that he was quite confused about, because he noticed that there was some kind of a peak in the data. And he spent a lot of time looking through the calibration of the data to try and understand what this variation was. You can't see it in this particular plot here, because this is really, the scale of this is to fit showing the transit in the entire plot. Jamie managed to convince himself that what he saw was not due to anything to do with the spacecraft. He had many people re-reduce the data, and he couldn't find any problems. So one thing which had been in the back of my mind, of course, was the possibility of reflected light, because I had written a lot about that before. There was a paper that was in one of the previous slides by myself and Dawn Gelino back in 2010, which specifically discussed the possibility of observing phase variations due to a planet in an eccentric orbit, because the phase variations they go as the semi-major axis to the power of -2. So it's very sensitive to the semi-major axis. But of course, when we're talking about an eccentric planet, you're not really talking about the semi-major axis. You're talking about the star-planet separation, since it's time-dependent. It also is linearly dependent on the geometric albedo. And in that paper from 2010, Dawn and I had an idea that planets in eccentric orbits would become dark when they pass through periastron. And the reason for that was that the evidence at that time seemed to suggest that planets which are close to their stars have very low geometric albedos. And the idea behind that was that a lot of the reflective condensates in the upper atmosphere are blown away by the insolation flux during the periastron passage. And so for that reason, I wasn't necessarily expecting to see anything from the MOST data, because I thought that the planet would become dark. So we wouldn't have sufficient precision to see anything. So what we ended up finding was that when we had a running average of the data during the periastron passage, we had this. This is showing the peak. Now, we were very, very unsure about this, because obviously the error bars are very large, and what we were really drawn to was the fact that the peak that we did see occurs exactly at the periastron when you expect it to. So what we did was we did an exhaustive Monte Carlo simulation which randomizes the data points to see if you would have a peak at that point. And that seemed to show that it was significant. But this is really digging into the data. But this was something that really caught us unawares. So what we're presenting this as is evidence of phase variations from this planet when it passes through the periastron. Now, remember that I said that Dawn Gelino and I had previously assumed that planets in eccentric orbits become dark when they go through periastron. And it turns out that I now think that that assumption is incorrect. And the reason is because of the time scale in which atmospheres can respond to this enormous change in flux during a short period of time. And the more eccentric the orbit, the less true that assumption becomes. Because for a case like this is an extreme case where the atmosphere really has no time to respond to the change in flux. And what that means is that the geometric albedo it has during the periastron passage is essentially the same as it has at apastron. Which means that if it's something like Jupiter with a geometric albedo of about 50%, then it has that same albedo during the periastron passage. So that could be a reason to explain why we see something where we weren't necessarily expecting to. So here's what we know about this star. As I mentioned, it's bright and it's fairly close, which is why we could do the work with Hipparchos and show that at least it's not in a face-on orbit. It certainly has the highest eccentricity of any planet that's been found so far. We've shown that it doesn't transit the host star, and I mentioned towards the end there about this raises some interesting questions about how atmospheres respond to these changes in flux. And this is something I've been talking to various people for a long time now. In particular, Adam Sherman and his group, people like Nicole Lewis, who worked with him, are now starting to model the atmospheres of planets in eccentric orbits as they pass through periastron to see what that reaction of the atmosphere is. So there's probably physics going on here that I'm not even really aware of, but it's something that we're putting out to the community because there are going to be, of course, other opportunities to observe this. Now, I mentioned before that because it's in a close to 18-month-day orbit, it can be difficult to try and follow this up for the next one. So the next two inferior conjunctions that are coming up, the next one is going to be later this year. It's going to be about the 3rd of September. And I've been checking various telescopes to see if that's doable. Unfortunately, Spitzer, which would be really great to observe this with Spitzer, Spitzer won't be able to see it at that time, which is unfortunate, because that would probably be the last chance to do it for Spitzer. I'm certain as to how much longer Spitzer will be operating, or at least eliciting targets for observations. The one after that, though, is going to be about 23rd of April in 2018, and that's very nicely timed to the launch of CHEOPS. And I think this could be a very compelling target for CHEOPS to observe just as soon as it's through its testing phase. And so that's the message that I'm trying to get out to the community now, because although we have plenty of time to prepare for the observations of the next inferior conjunctions, this is a difficult target, and this is a pretty small signal to try and observe. So it does require some thought. I will finally let you know that the details of this are in the paper, which has been submitted to APJ. The paper was submitted to APJ just before the Extreme Solar Systems meeting, and I received a favorable referee report just before Christmas. I noticed that a lot of the referees seem to be getting their reports out right before Christmas, so that they don't have to worry about it over that time. We've just submitted the response, so that will be accepted pretty soon. But all the dates and details are in that paper. So that's the end of the presentation I had for you, and I would be happy to answer any questions.
Well, thanks a lot, Stephen. That was very interesting. It would be great if CHEOPS could observe this. Of course, CHEOPS also has some constraints in what targets it can observe, so and so on. So we have time for questions. So are there any questions? I think, I guess you just asked it, if you have any. Are there questions? Don't forget to unmute your microphone in case you have, otherwise we can't hear you. Christoph.
Yes, I had a question. So have you tried to estimate the time space on which, let's say, clouds are being vaporized at this moment?
No, that's exactly the kind of thing that I'd like to know. I have not produced in the paper. We don't do any detailed modeling like that. That's the sort of thing that I really need to talk to folks who do that kind of atmospheric modeling of clouds to see if that kind of timescale is even possible. Because my understanding is that it's the difficulties there are the degeneracies with things like a pseudo-synchronous rotation, how that will affect the recirculation of the heat that's been that's been absorbed during the periastron passage and the advective timescales of that. So that's something that I have not calculated, but I am talking to various people about trying to understand that better. Sorry about those weird noises. I have two cats which are chasing each other, and since it's 2 o'clock in the morning, they're particularly active.
Night animals. So I have a question. Is the age of the system well known?
I can't remember what the age of the system is. We do have it in the paper. My recollection is that it's similar to the Sun, several gigayears, but that detail is in the. We have a lot of the stellar characterization details in the paper. We obtained additional spectra for this target, but those details are in the paper. But my recollection is that it's not anything unusual.
No, I just figured it would be interesting for the dynamics of the system. So you mentioned Hipparchus. You mentioned Hipparchus also, and I mean now we have Gaia coming up. I'm guessing Gaia will be able to determine this orbital characteristics quite well.
Yes, that is true. That will place a lot more constraints on what the true mass of the companion is. That will be very interesting because the constraints that we have on the mass, as I said, the M sin I is about 1.5 Jupiter masses, which means that it has to be very close to face on in order to be in the brown dwarf range or something like that, which it could well be. But Gaia will do an amazing job of constraining that a lot better. So I'm looking forward to that very much. Another thing I wanted to mention is that regarding the eccentricity is that, I mean, this planet being in such an eccentric orbit, these kinds of orbits always fascinate me because to me it's kind of like looking at the blood splatter from a murder scene. You know that something bad has happened, but you don't know exactly how, and so you try and think of all the possibilities, the orbital dynamics which could result in such an eccentric orbit. And one of the things to note is that 20782 is part of a wide binary with 20781, and so I was thinking about ways in which you could have planet-planet scattering that would produce such an eccentric orbit. That's very, very difficult to simulate, very difficult. But with a wide binary companion, that opens up many other possibilities with
like Kozai migration.
Kozai, yeah, exactly, yeah.
Okay, are there other questions? Now is your chance. Otherwise, I'd like to thank Stephen again, and I hope you have some good sleep after this.
No, it's my pleasure. Thanks for inviting me, and I look forward to talking to you more in the future. I'm going to be at the next CHEOPS meeting in Geneva.
Oh, so excellent. Okay, great. Okay, thank you, and goodbye, everyone.